environment. If there is not much gas, black holes grow through gas accretion, mergers, and tidal capture of stars. Out of these three, the most dominant way to grow them is the accretion. So in order to grow them, you need to have the available gas to feed them continuously. But there is a limitation to the growth of a black hole, theoretically. Because when the black holes accrete, they produce radiation. Then that is the balance between the radiation that comes from an accreting black hole towards the accretion. So the radiation pushes the gas away, and the gravity of the black hole brings the matter towards it. So the balance we call Eddington limit, and that sets us how quickly, how fast a black hole can grow. So if you have a massive black hole seed to start to life, and enough gas available for it to accrete, then the ones that we have seen so far are at redshift of 6. We talk in redshift space, but it's basically 700 million years after the Big Bang, has like 10 billion times the mass of our sun. If you look at the galaxies nowadays, in our time, we do not see much more massive than those ones still. The Milky Way galaxy, our own, has 10 to the 6 solar mass, black hole at the center. So
there's no transformation that could occur with a black hole at some point because it gets so big that it changes into something else. That's where I was
black hole is black hole forever. As far as we know, once a black hole, always a black hole. Because I see them as a energy powers of the universe. They accrete everything, they turn everything into energy, and they keep them inside. That's how I see them. They are the energy powers of the universe.
Well, there is Hawking radiation that might.
Yes, but once they are big enough, because the Hawking radiation scales with inversely with the mass. So if you are small, then you will evaporate. But if you are big enough, then.
But so you were talking about the primordial black holes before that are extremely low mass. Wouldn't they have evaporated by Hawking radiation?
Yeah. So if the initial mass of them is more than 10 to the minus 15 gram, at that time they will lost
10 to the minus 15
of the Hubble time. Yes.
That's pretty small.
That is very
because that you can calculate with the volume of the universe at that time. So that is the number of measurement.
Neil.
Is any progress being made vis-a-vis dark energy and dark matter?
There is a paper from yesterday about the dark matter,
Oh yeah?
saying that we may not need a dark matter.
What?
Oh, this is long.
The story.
Modified.
No, not more. The story that it's like, I don't know how much you know about the history of the dark matter. It's an observational property. So they were looking at galaxies and the rotation. And they were saying that with radius, how much of gas is there, and they're looking at the velocity curve of it. And with over radius, it should go down because there is less gas at the outer skirt of a galaxy. But when they look at the observational data of this velocity curve, they say it's flat, meaning that there is a large amount of gas that we don't see. That's why they call it dark matter. There is a matter they must have that provide the flatness of this velocity curve, but we do not see it.
But now there's a lot more evidence for dark matter than just this. So we can tell, for example, we know that light bends due to mass. This is a property of, this is something general relativity tells us. It was one of the first measurements ever made that confirms general relativity. And now people routinely measure the bending of light due to a galaxy from the stuff behind us. Or the light is emitted from behind and then the galaxy bends the light. And we can tell that basically the amount of mass that the galaxy has that's bending the light is way more than the mass that could be accounted for by all the stuff in the galaxy that's glowing.
I think a fair answer to Neil's question is no. There's still progress. People are still looking for it, but nothing has been found, and there are still, as the paper that Aichin quotes, there are still some skeptics about the need for it, well, the jury's still out.
And there's some theories that say that all of dark matter, part of dark matter is actually made up of those primordial black holes. But
Yeah, true.
that's,
Yeah. There was a
How
question
how
over
well
here.
do these two numbers match?
Wait.
Well,
You mean
the
like the rotation curve
yeah,
and
the
the
mass
thing?
from the rotation.
Exquisitely.
Oh, okay, all right.
As do other measurements. So there's a huge body of evidence that there's something we're missing. Either it's more stuff, or our understanding of gravity is wrong at large scales. Those are essentially the two possibilities.
How about small, dense things that are cold?
Yeah, so I mean that is essentially what dark matter is.
Well, but you know, why couldn't it just be things between the size of Jupiter and,
Well,
and a
It
small star?
can't be made of ordinary matter, ordinary baryonic matter, because then that skews the nucleosynthesis that took place in the Big Bang. There's several constraints on the amount of baryonic matter that could have come from the Big Bang in order to produce the observed abundance of helium and the other light elements that were produced in the Big Bang. So you simply can't have more baryons than we account for in the light matter, and so the dark matter has to be something exotic, non-baryonic.
So going back earlier, what you said was when we did this detection with the gravitation, that you saw it much more frequently. It seemed to me that what you were saying was this occurs a lot more frequently than we ever knew. Where the creation of black holes may be a very common occurrence.
Well, so the jury is still sort of out about that. There's a question of where the masses of the black holes are going to fall and what their sources are. I think one thing that's sort of is a confirmation of what we expected is that we are seeing many mergers of black holes of about 10 solar masses each, and this is a reasonable expectation given the number of stars that are massive enough to produce this kind of black hole, and the amount of volume of space that we are able to currently search, for example. If the question of the mass gap, I think, is more interesting. Yeah, it's possible that these things are out there and we just didn't have the tools to see them.
and I think it should also be pointed out that the rate at which we have observed binary black hole mergers and neutron star mergers is within the range that we expected to see them. Now, the range that we expected to see them is huge, like a factor of 1,000 or so, because it depends a lot. The main question is how are these binary systems formed, and that's something that we do not understand very well. So our expectation was like, okay, it could be this or it could be 1,000 times more. Well, we observed this somewhat in the middle, so that's in some sense a good thing. I think what maybe was a bit of a surprise is how early we've actually observed them. But the rate at which they're happening is not a huge surprise at this point.
It's a weak confirmation of our expectations, in other words.
Yeah, but with time, this will get a lot better because as we observe more of these things, we're going to get a much better handle on what the actual rate is, and then that's going to be great because that's going to tell us how to inform our models of how binary star systems evolve. So in the future, the answers are going to get a lot better, and it's thanks to the fact that we can now see these things.
I think a big surprise from the very first detection of a